Okay, hi, welcome back. So today in class we started looking at the log function as a graph. We started with an exponential, and then we took the inverse, which was switching the x and the y, and plotted those points then on the same log function. And of course this is what that graph looks like, y equals 2 to the x. I have put the table over here, just in case you wanted to again take a look at these values. But we've looked at this graph several times now, and we know that it goes through this point 0, 1. So now what I'm going to do is I'm going to graph its inverse. And we know from back when we did functions that the inverse simply switches the x and the y. So I'm going to do that. And if you look now at the second chart of values, all I did was take this x column here, this column of x's, and move it over to the y column. And I took the column of y's and moved it over to the x column, thereby switching the x and the y and creating the inverse. If I graph that now, this is what I end up with. It is the inverse, also called the log function. Notice on the original, we go through the point 0, 1 because it's an exponential, and anytime x is 0, anything to the 0 power is always 1. Well, when I switch the x and the y, this graph is now going to go through the point 1, 0. Keep in mind, on our exponential function, my domain over here is all reals, whereas my range, and we've looked at this before, but I'm going to put it down again, for the exponential, is just the y's greater than 0. Now when we take the inverse, the domain and the range actually literally switch. So now the domain on the log function is the x's greater than 0, and the range will be all reals. Okay, as far as an equation for this goes, what I could simply do is switch the x and the y and say x equals 2 to the y. This is actually considered an inverse function, well, an inverse to the function y equals 2 to the x. As soon as you switch the x and the y, you have the inverse. What you need to be careful of, though, is that this is not in function notation. And so that's where the real problem comes in, because I can't put this in my graphing calculator to have the calculator graph it for me. In order to do that, it has to be y equals. Well, the y is in the exponent. And so this creates a whole new problem for us. And this is where log notation comes in. And so if we go to the next screen, what I have here is the actual log notation, which is necessary for us in order to put it into function notation so that this can be graphed or whatever it is we want to do to it. Okay. What you need to understand is that these two formats here are equivalent formats. They actually mean the same thing. However, this one here is in exponential form. This one here is in log form. And you can hopefully tell the difference between those. The log form actually has the word log. The exponential form has a base raised to an exponent, exponential form. But these are the same thing. And so one of the things that we need to do is get comfortable going back and forth between these two formats. Okay? So that if I had something like this, what I could do is tell you that the log base 2 of 8 equals 3, or 3 is equal to the log base 2 of 8. Let's say that this was given for me. I could put this into exponential form by understanding that this base right here, log base 2 of 8, that base is the base on the exponential, but that this 3 actually represents the exponent on the exponential because that corresponds with the y, and the 8 represents the x, or over here, the answer. And when you look at it in exponential form, you can see that this is definitely a true sentence because 2 to the third is equal to 8. Okay, but again, these are equivalent formats, one in exponential form and one in log form. Let's try another one. So I'm going to look at this one and I say log base 4, and that's how I'd read this, log base 4, it's subscripted, of 16. I can figure out what that equals, and I know that it equals 2, because I know that when I find the log of a number, and that's what this is, the log of a number, I'm looking for the exponent. This 2 represents the exponent on this base. So the log of 16 is going to be 2 as long as the base is 4. And that is because over in the exponential form, the base is 4, the exponent is represented by 2, and the 16 is the answer, or the number that it's equal to. And you can see again that that is a true sentence. So in very general terms, if I tell you that the log, any base, I'll call it base b, of a number, any number is always equal to the exponent, and I'm going to put e. So the log of a number, and that's how I read this, the log of a number, you're finding the exponent. When you take the log of a number, you're finding the exponent on the base of choice. Okay, so this is your base. You're taking the log base b of a number, and then you're looking for the exponent. Logs follow exponents. And so what I like to do is call this Ben. And I'll show you in a minute. When I'm writing this in exponential form, the base on the log is the same as the base on the exponent. So whatever goes here also goes over here as the base. What you need to remember then is that these two pieces here, the n and the e, and what I'm going to do is swap colors. The n and the e switch sides over the equal sign. So if that's my equal sign, here the base and the number are next to each other. Here the base raised to the exponent is next to each other. And then the number goes on the other side. And this is what I like to call Ben. Okay, and so we're going to talk about Ben. The base raised to the exponent equals the number. And so when we look at solving log equations, Ben here is going to help us solve these log equations. Now, when you're solving a log equation, of course, there has to be an unknown. And so what I would tell you is let's just throw down a couple and see how it goes. And I'll just go do an example of each. So let's say I have the log base 2 of some number, I'll call it x, and I'm going to tell you that the answer is going to be 4. So in order to find x, which is what I want to do, I want to find x here, I'm going to solve this log equation by putting it into Ben, or exponential form, knowing which role each of these three parts holds or plays, okay? So of course the base right here is my 2, and then the exponent comes from the 4. So 2 to the 4 will equal my number x. This is easy now. Now it's just a matter of plugging that in your calculator or whatever, and 2 to the 4th is 16. So here we have another example. Log base 4 of 8 equals x. And so if I put this into exponential form, or what I like to call Ben, again, remember that the base on the log is the same as the base on the exponential. So that's 4. And then I have to skip to the other side of the equation to pick up the exponent. So 4 raised to the x is going to be equal to, circle back around, and you set it equal to 8. Now this is an exponential equation, and this is where we were a couple days ago with solving exponential, where you find a common base. And so the common base I'm going to use in here is 2. I would take each of these to base 2. And so 4 becomes 2 squared, and 8 becomes 2 cubed. And keep in mind that x was already there on the 4. And so now I'm going to solve the equation 2x equals 3, which means x equals 3/2. And that's my answer. Okay, the third kind of example is when the variable, the unknown, is the actual base. But I'm still going to solve it the same way. It's still a log equation, so I'm going to pick out the roles of each part, remembering that this is the base, this is the exponent, and this is the number. And so I'm going to write x to the second power equals 25. And now I have a power equation. If I square root both sides, I will break it into x equals 5. And that's my answer. We can get a little more complicated or fancy if you want. It doesn't really matter. But every single time I have this log equation, I'm going to figure out my roles. And of course, this is my base, this is my number, and this is my exponent. And so when I rewrite it, I'm going to write the 3 as my base. My x plus 1 becomes my exponent, and that's equal to 9. Again, I have a common base that I'm going to go for. I'm going to rewrite my 9 as a 3 squared. And so I will have 3 to the x plus 1 equals 3 squared, which means now my exponents, x plus 1 has to equal 2, and x will equal 1. I can move this unknown around as much as I want. I can give you a weird one, like I can make the base equal to something like x plus 2. It really doesn't matter. And then I'll say x plus 2, let's say 16 equals, I don't know, 2. And so what I would do then is, again, assign my roles. And this is my base, and this is my number, and this is my exponent. And so my x plus 2 would get raised to the second power, and that would be equal to 16. So when you square root both sides, you will end up with an x plus 2 equal to 4. And of course, x would equal 2. Okay, so it doesn't really matter if the quantities are monomial, such as this 3 or this 9, or if they're binomial, here or down here as a base, or even in here as a number. Just follow the rules. It's about assigning the parts, knowing it's the log base b of a number equals the exponent. So the log, the base number, exponent. And when we put it into exponential form, it's the base to the exponent equals the number. That's what I call Ben. Okay. So tomorrow we're going to practice just putting these equations from log equations into exponential equations so that we can solve them.